All right, let's see how the solution comes out. So in order to start, I'm going to go ahead and find the two U values that I need. I know they're going to be two different velocities, one for each pipe diameter. I know the formula for U. Hopefully at this point you do as well. It's going to be m dot divided by the area times the density. So I'm going to have U1 is that. I know all these values, so that's easy. My mass flow rate is 30 kilograms per second. A1 and then 1,000 kilograms per meter cubed is my density for water. I need A1. Okay, A1 is equal to the diameter 0.035 meters squared times pi over 4 is equal to 9.62 times 10 to the minus fourth meters squared. There's my A1. I plug that in to my formula here, and I get that the average velocity for the smaller diameter section of the piping is 31.2 meters per second. So there's my first velocity. For U2, I have a larger diameter pipe, so I'm expecting a slower velocity. So just say that out loud. Make sure you use your engineering common sense as you do these numbers when you punch things into your calculator. Make sure that things come out the way you expect them to, or the way they have to from a physical point of view. So we have the same formula, of course, except A2 has changed. A2 is now the larger diameter, 0.08 meters squared times pi over 4, which is equal to 5.03 times 10 to the minus 3 meters squared. When I plug that in, I get an average velocity of 5.96 meters per second. So those are my two velocities. And now I'm going to just check to make sure the system's turbulent. Now, I am virtually certain it's going to be turbulent, but I am going to check, and that's slow. Anyway, I'm going to need the Reynolds number if it is turbulent, because if it is turbulent, I'm going to need the friction factors, and in order to find friction factors, I need to have these values. So we have 31.2 meters per second, 0.035 meters, 1 times 10 to the minus 6 meters squared per second, and that gives you a Reynolds number of 1,992,000. That's really not enough. That's too many digits, but at any rate, about a million. And then we have the Reynolds number for the second diameter, 5.96 meters per second times 0.08 meter diameter divided by 1 times 10 to the minus 6 meters squared per second, and that comes out to 477,000. So very, very well beyond what we need for turbulence. Of course, turbulence in a pipe is 2,000. So they're both extremely turbulent, no problem there. So we're good to go with our formula. So our formula for turbulent pipe flow that has multiple diameters is delta P plus rho G delta Z is equal to 1/2 rho U1 squared times L1 over D1 F1 plus 1/2 rho U2 squared times L2 D2 F2 plus 1/2 rho U1 squared times the loss coefficients related to diameter 1 plus 1/2 rho U2 squared times the loss coefficients related to diameter 2, the sum of all those loss coefficients related to 1 and 2. I'm going to need the sudden expansion coefficient. For that I have a formula, sudden expansion formula. That's 1 minus the little diameter over the bigger diameter squared, all of that squared, and that comes out to 0.654. So that's one of my coefficients, and that's associated with the first velocity because the first velocity is the larger velocity. That's the velocity related to the smaller diameter, and for the sudden expansion loss coefficient, we are supposed to use the velocity from the smaller section along with this k. So that's going to be a k1. So the sum of k1s are going to be the 0.654 for the sudden expansion, the 0.6 for bend 1, and the 0.7 for bend 2. So if you look back at the image, at the picture of the system, these things all happen with diameter 1. The first bend, the second bend, and then the sudden expansion are all related to the first diameter. So they're all part of K1. And so the sum of the K1s is equal to 1.954. All right, so then the K2s is just, I only have two. I have 4.0 for the half open valve, and then I have 1 for the exit. So that's it for the K2s. So obviously the sum of the K2s is 5. So that's pretty easy. So now I have my formula here. I know my sum of K1. I know my sum of K2. What I don't know yet are F1 and F2, right? So that's what's going to have to be sort of the next step. I need to find those F values. So for F1, I need F1. So I need RED1, and RED1 we said was about $1 million. It's 1,092,000. But I'm going to be looking on the Moody diagram, so I'm not going to be worrying about that 92,000 on that chart. It's going to be very hard to see anything that accurately. So I'm going to be using $1 million there. I need my epsilon over D1. Well, my epsilon was 0.002 millimeters. That was in the problem statement. We might not have highlighted that earlier, but it was in there. So right here, epsilon was 0.002 millimeters. So we have the 0.00 over the 3.5. This is for D1, the 3.5 centimeters. And of course, we need to put that over the same units, 002. I'm going to go to all millimeters and 35 millimeters. And so that gives me 6 times 10 to the minus 5. And I look on the Moody diagram, and I found, when I looked on the Moody diagram for those values, 0.0125 for F. So there's my F1. So I looked on that diagram, million, 6 times 10 to the minus 5th. I thought it was about 0.0125. Now I need F2. For F2, the Reynolds number based on the second diameter is 477,000. And I need epsilon over D2. And it's going to change because D2 is not equal to D1, right? So I have 0.002 millimeters divided by, in this case, 80 millimeters. And that gives me 2.5 times 10 to the minus 5. So that's a different epsilon over D. I have my Reynolds number. Again, I go to Moody. I follow that line, and I found that F was about 0.0135. So a little bit different, slightly different Fs for that section 1 and section 2. So that's my section 2. I got to put all that together. I also need my delta Z. Well, my delta Z is equal to Z in minus Z out. That's our definition of delta Z for these problems, and that's minus 5.4 meters because the Z out is greater than the Z in. The pump is pumping uphill. So I can write all of that in terms of my pressure now. So delta P is equal to 1/2 times 1,000 kilograms per meter cubed times U1 squared and all the things that are associated with pipe section 1. So I have the length of pipe 1. This is my L1 over D. 0.035 meters, so that's L1 over D1, times my friction factor 1, 0.0125, plus all my sum of the K's, my sum of K1s, 1.954. That's the first term. The second term, which is added to it, still 1,000 kilograms per meter cubed. That didn't change, but now U2 squared instead of U1 squared. Of course, the new pipe length is 10 meters of the second diameter pipe, which is a 0.08 meter pipe. So that's my L2 over D2. Now I multiply that by F2. 0.135 is my F2, and then I add my sum of the K's for that section, which is the 5. It's larger because it has the half-closed valve. Finally, I have rho G, and then delta Z is 5.4, which is no longer negative because I moved it to the other side of the equation. All right, well, I have all this stuff. And I plug in my U1 and my U2. My U1 is 31.2 meters per second. My U2 is 5.96 meters per second. So I plug those in. Rho and G, of course, that's 1,000 kilograms per meter cubed, and G is 9.81 meters per second squared. So I put all of that together, and I plug it all in, and I got 1,995,552 for the first bit. Then 118,820 for the second bit, and finally 52,974 all newtons per meter squared for the rho GZ term. So my biggest term by far is the first the first one, the one that included the sudden expansion and 2 bends, but mostly it's big because it has a very large velocity, a lot of velocity in that pipe, leading to a lot of frictional losses in the pipe there. So we have a big loss there. And if you add all those up, and you get the total pressure that has to be supplied by the pump, 2,167,000 newtons per meter squared. So that's what we have to deliver with that pump if we're going to pump that amount of water through the system. Of course, I was asked actually to find the power, and the power we said was equal to the pressure that increase times the volumetric flow rate. Well, the volumetric flow rate is just the mass flow rate, so kilograms per second, which was given, divided by the density. So that's kilograms per meter cubed. So that's easy, it's just 0.03 meters cubed per second. So that's simple, 330 divided by 1,000, 0.03. So we multiply that 0.03 times that 2 million, meters cubed per second times that 2.167 times 10 to the 6 newtons per meter squared, and we get the answer, which is that the power required, the minimum power required to make this pump do the job as described to deliver that 30 kilograms per second of water is about 6.5 times 10 to the 4th watts, or you could write it as 65 kilowatts. So 6.5 times 10 to the 4 watts, or 65 kilowatts, is the minimum energy required to pump that water at that rate up through that pipe network. And mostly, we were able to show that even with a complex pipe problem, pretty easy to do. Just got to find those loss coefficients, just add them all up, put them together with their right velocities. Each one has to go with the correct velocity, and you can just add it up to get those pressures.